I thank, of course, the organizers for inviting me, and I'm very happy to be in this place. Very beautiful place. Now, I'm not sure that you can actually see on the screen. Can you? Oh, it's okay. So as you see, it's going to be about Markov loops. So I suppose you all know what is Markov because we are in Markov's country, and what are loops. So we'll start, and mostly during this talk, I will talk about processes on graphs. So you all know, I think, what is a graph. So you have a set of vertices and a set of edges between the vertices. So we have to think of graphs as the most simple example of topological space. So it's what is given essentially is a topology when you have the graph. And so the most simple example is a complete graph where you have all possible edges between the finite set of vertices. And lattices. There are also examples such as trees. And all these graphs, in a sense, are related one with each other, especially via the operation of coverings. For example, when you take a finite graph, simple graph, then the universal cover is a tree. And in between, you have all kind of intermediate coverings, such as lattices, etc. So there is a full topology about these graphs, but we'll just consider mostly either the general situation, either simple ones such as a complete graph or Z or a little bit Z2. So once you have the graph, you consider, so the graph is a topology, and then you have to think of metric. So in graphs, metrics are given by conductances. That is, you put a weight, a positive weight, Cxy, on the edge between x and y. And so this is related, of course, to the theory of electrical networks. So this is well-known relation between the theory of Markov chains and the theory of electrical networks. For example, in the book of Doyle and Snell, it's well explained. It's a simplest situation in which you can see the relation between potential theory and Markov processes. Now, in addition with conductance, we will also consider a killing or equilibrium measure, which in a sense can be viewed as the possibility for the Markov chain to get killed, or it can be viewed as the conductance between the point x and the Earth. There is a symmetry point if you look at things from the point of view of Markov chain, which is the Earth if you look at it from the point of view of electrical networks. So these are the two basic parameters. So I'm considering only a reversible case. It's not, well, it's not essential, but I will consider this case. And then with this, you have a duality measure or speed measure, which is obtained by taking the sum of all conductances coming from points coming from edges starting at x, and add the killing measure at that point x. And then you get a transition matrix, which is in general sub-Markov, by normalizing the conductance Cxy by lambda x. So this is a Markov or sub-Markov if when the killing measure is strictly positive. So you can often, we consider the conductance on the graph to be 1, but there is really a point for not taking this to be 1, is that one of the things which is useful to do when you try to compute things is to vary, to let the conductance vary. So it's important for that to consider the general case. And then all this can be summarized with the formula of energy. So the energy of a function is given by taking the sum of Cxy over 2, the quadratic variation, f of x minus f of y squared, and add the L2 norm according to the killing measure. If you have any questions about this, please ask me. So that will be the basic setting. In fact, we'll also consider, without being too rigorous, scaling limits. So as explained in Greg Lawler's talk this morning, well, when you have an open set for example, here in the plane, you can actually take a grid, and when you let the mesh of the grid go to 0, this more or less converges. And so when you take the discrete energy I defined before, you see, with the quadratic variation, in fact, the quadratic variation f of x minus f of y becomes a gradient. And this gradient, of course, if I take here unit conductances, it will be the gradient, the usual gradient. But if I take conductances which are not the usual one, which are not units, that I will be, in general, a Riemannian gradient. So, and I will get a Riemannian measure too. So this is how you can, at least intuitively, go from the discrete to the continuum. So, as I already said, when you have such a system of conductances and Killing measure, you get a Markov chain in discrete time. But for our purpose, it will be useful to consider actually the continuous time Markov chain, so which is essentially the same as the discrete one, except that you allow holding times. So it means that before jumping to another site, you wait for an exponential holding time. So from the analytic point of view, this means that instead of using the transition matrix P, you consider a transition semigroup PT. You can compute as the exponential of T, P minus identity. I suppose that most of you have already seen this. So P minus identity, this is the Laplacian associated with the situation, the geometry. And this is the heat semigroup, in a sense. See? Now, so this is analogous. If you take the scaling limit, what you will get here will be Brownian motion. So with this semigroup, you can define, a bridge measure. So I don't write what it is because I suppose you already know. So it's a measure on paths going from x to y. So I'm taking discrete space, but sometimes I will draw pictures in continuum because it's easier to see what is a path. You can imagine there are pixels anywhere on the screen. And so on paths from x to y, there is a natural measure given by a Kolmogorov formula using the semigroup, which is on path from x to y and given by the semigroup PT. And the point here is that I don't normalize the measure. So the measure total mass is given by the transition PT from x to y. We have to normalize by lambda y, so that this is a duality measure, and this normalization makes that actually this is symmetric in x and y. If you don't do that, it's not. Of course, often this measure is actually constant, so please don't pay too much attention to that. All right, so we have this bridges measure. Now, with the bridge measure, you get the loop measure, which was already defined essentially by Greg Lawler this morning, but here I do it immediately in continuous time. So this is inspired actually from the loop measure, which was defined in a Lawler and Werner paper for the two-dimensional Brownian motion, and earlier you can find already such things in Simonsik's old paper in physics. So this measure is obtained by taking the bridge measure from x to x, so x is a base point, and then take all possible times and integrate with respect to 1 over t. Then sum in x with the duality measure lambda x. Then, as it was explained to you this morning, this gives a priori a measure on based loop. So you start at x and come back to x. But in fact, you are not interested in the observables or random variables depending on the base point. So actually you look at the image of this measure on loops. And so then this measure will be invariant under translation by time. So for that, you have to be precise that this actually, it's about the time and not about the position that it is translation invariant. So you have the same formula, as I said, if you consider continuous spaces with semigroups and duality measures. You can actually write exactly the same formula, except instead of having a summation, you have an integral. And this is with such integrals that the loop measure was defined this morning for two-dimensional Brownian motion in an open set. Now, since here we are on a discrete space, let's think a little bit how really these loops work. So I just draw a picture here to let you understand. So a priori, a loop can have multiple points. It doesn't have any origin. And in the discrete space, it will be a certain number of points with an order between the points, and you can come at one point once and then come back. Oh, I noticed that, yes, okay, this is like that, right. And each time you come to a point, you stay there for a certain exponential holding time. So I drew the exponential holding times like with these red segments. And you notice that for that point, you spend 2 exponential holding time at this point. So this is actually the space of loops we consider. And you have to think of when you consider the base loops, it means that you choose the base point uniformly on the red intervals. Now, with such a definition, you have to face the fact that there are trivial loops, namely loops where you give yourself a point and a holding time. So it could be that there is no jump on the loop, because the semigroup PT, when the time is very short, if the duration of the loop, which is t integrated in 1 over t, is very short, well, it's likely that there will be no jump. So, in fact, if you think of let me show you again the definition. You see, this has infinite mass because there is an integral from 0, oh, there is a mistake here, sorry, it's 0 to infinity, sorry. So anyway, because of the 1 over t near 0, this has infinite mass near 0. It means there are infinitely many loops with very small duration, and they will be trivial loops. Sorry. So the measure of these trivial loops is infinite. When you go to the scaling limit, there is no more trivial loops. In a sense, you can think of these things backwards. Namely, if you discretize the space, you see that very short loops will become point loops. And so the measure of very small loops is always infinite in the continuum. But the measure which have n jumps, you can easily compute from the definition what is this measure, and it is a finite measure. And so it will be 1 over n, the trace of the transition matrix to the power n. It is, okay, I don't give the proof, but it's not hard to guess that it should be that, because 1 over n, because the starting point is random, is not decided, and the second thing is p to the n, you have to take a trace because you come back from where you started with. Then if you look at the total measure of non-trivial loops, this will be the sum of these terms, and as you see, it will be the trace of minus the logarithm of I minus p, logarithm in matrices. You can also write as minus the logarithm of the determinant of I minus p. Of course, this type of formula would have more difficulty to hold in the continuum. Now, let me finally introduce another object which is important, is the green function. So the green function is just the integral, essentially the potential, so the integral of the pt for all times, so for t between 0 and infinity. And then again you have to divide by lambda y so that this will be symmetric in x and y. So in the continuum, the potential operator is a probability kernel. Here we want a function. So in a sense, we take a density with respect to the duality measure. Now there is another way to write this integral. Since this was an exponential, you see you can integrate an exponential. And what you find is that this will be a diagonal matrix with entries given by the duality measure. So this is lambda, the diagonal matrix formed by the elements lambda x minus the conductance matrix, and take the inverse. Now I can rewrite with this notation the measure of non-trivial loops, and you see that this is the logarithm of the determinant of the green function divided by the product of lambda x, namely the product of the elements of the duality measure. Let me give you an example, two examples actually. If you are on the complete graph, so with unit conductances and constant killing rate, then the green function is given by this formula, 1 over c n plus c plus 1 over n plus c when you are on the diagonal. I'm sorry, I see that there are some missing. There is a little imperfection in the system, but this should be delta xy, sorry. This should be the diagonal constraint. And if you are on integers with unit conductances also, but kappa 1 equal 1, so this means that the Markov chain is just the simple random walk killed at 0, then the green function is given by Gij is 2I infimum j, as it is well known. So I don't know how to remove this. Okay. So when you have a Markov chain, you can kill it out any subset. So you just kill the Markov chain when you get out of a set D. Then it changes, of course, the transition matrix. So it's a restriction of the transition matrix to D cross D. And it changes the energy. The loop measure will be the restriction of the loop measure to the subset D. And the green function, now it's not the restriction of the green function, it's actually you take the inverse of the restriction of the inverse of the green function. So in a sense, this is like the generator, and you take the generator is the restriction of the previous generator, but the green function is the restriction of the inverse of it. So as I said, the loop measure is just the restriction. And then only for such consideration plus some exclusion-inclusion principles, you can already get some result about the measure mu. So for example, you can evaluate the measure of loops which connect two sets. So this set I call D1C because I'm interested in its complement, which is D1. So this is the complement of D1. And this set I call D2C. Then the measure of the loops which connect the two is given by logarithm of determinant of the green function, determinant of the green function of this set, which is a complement of the union of these two green sets, divided by the determinant of GD1, determinant of GD2, where D2 is a complement of this one, and D1 is a complement of this one, and D2 is a complement of this one. This is just because we know what is the measure of non-trivial loops, and we apply it to 4 different situations and do exclusion-inclusion. So this is really not difficult to obtain. Now, another classical thing is Feynman-Kac formula. So Feynman-Kac tells you what happens when you do additional killing. So I have two notations. The first one is, so when you add a measure chi to the killing measure kappa, the Green function is modified, well, in a trivial way. You replace lambda by lambda plus chi. And you have here what is properly called Feynman-Kac formula, namely that the exponential of this semigroup with additional killing is obtained by the expectation for the bridge measure of this penalization factor, which is the exponential of the integral from 0 to t of chi over lambda of xs ds. So this is usually called Feynman-Kac formula in the context of Brownian motion, but it is true for any reasonable Markov process, and especially for this discrete Markov chain we consider. Now, let me give a result about the occupation field. So when you have the loop, to each loop is associated an occupation field. Namely, it's essentially the time spent by the loop in any point. You see that the loop can go several times through a point, and so you add up all these times. Then you have to normalize by this lambda x again. So we can find, this is not really a distribution because mu is not a probability, but we can find the measure, some kind of Laplace transform, except there is this -1 here to avoid divergence, of this occupation field. So you integrate it against an arbitrary measure chi, and you evaluate mu of it. And this will be minus the logarithm of the determinant of the perturbed Green function divided by the determinant of the Green function. So the idea is to vary the killing measure, and it gives you, well, it's kind of equivalent of this Feynman-Kac, but in the context of the loop measure. Now, this is a quotient of determinant, and I want to write it in another way. The reason is that we want to go beyond the situation of the finite space, and you see that determinant of Green function will be it will be difficult for them to exist on infinite spaces, even discrete. So, in fact, this quotient of determinant simplifies and can be written as determinant of identity plus m multiplication by square root of chi, Green function multiplication of square root of chi. And so this is a perturbation of the identity, and the identity as a determinant. So this will not always exist, but it will exist more often than the determinant of the Green function. This will exist when this operator is trace class. So I don't know if I actually have time. I had planned to give a proof of this, but maybe I can have a look. So this formula will be of some importance, so let me call it P2. So how do you prove such a result? I'll go vaguely. So we want to compute this quantity, which is a kind of Laplace transform of the occupation field. So we just write what it is by definition in terms of the explicit construction of mu. And as you see, here you see the expression that occurs in Feynman-Kac formula. Now, so we can use Feynman-Kac formula to express it as a semigroup with generator P minus I minus this multiplication matrix. And then because there is a minus 1 here, you have this, which is just the weight of this measure. So this is fairly trivial. Now, you have to sum in X. And what you do is you notice that there is here an integral in T. And there is T identity. So you can actually take out the identity and put this prefactor E minus T. And then you can expand the exponentials. So when you expand the exponentials and take the sum in X, you find sum of traces of powers of transition matrices. So you get this T over K factorial, which come from the expansion of the exponential. Then you can perform the integration in T thanks to this factor E minus T and to the TK, and you get traces of powers of these transition matrices. So perturb 1 minus the original one. But you have an additional factor 1 over K because when you do the integration, there is a 1 over T here, which comes from the definition of the loop measure. And since you have a 1 over K, you see that again you see a logarithm. There is a sum of powers with factors 1 over K, which gives you logarithm. And so you find a fairly simple formula, trace of logarithm of 1 minus P minus logarithm of 1 minus P perturbed. You can write it in a similar way by multiplying by lambda, so this is just the same thing. And then you can express this again because G is the inverse of M lambda minus C in terms of logarithm of G. And so trace of log is a log of that, and you find this formula, this quotient of determinants I had previously. Now, to get the other formula, namely, this one. So this is a quotient of determinant, but I want this one. So what you use is this is just the resolvent equation, except that it is true even if chi is not constant. See, you have this formula. It's an easy exercise, and so from this formula you get that you can multiply by g chi minus 1, and you get that the determinant of g chi minus 1. This is exactly I identities plus g m chi. And now you may notice I wrote it I wrote not g m chi, but I wrote this. So in fact, well, you can do this easily, but why do you do this? Because you want this to be symmetric. You see, determinant are somehow, for operators, it's a bit nicer when they are symmetric. So, but just by making a simple conjugation, you get this formula. Now I finally come to the main topic, namely these Poisson ensembles, called also loop soups. So, as I said, introduced by Roland, Werner, and Szymanczyk. So it's a Poisson process. So I take here space-time Poisson process. So my space is a space of loops. And you imagine that loops are falling on the space. So loops are falling. So you have to give you an intensity measure, a rate at which they are falling. And this will be, in time, it will be the measure, Lebesgue measure. And in space, so in the space of loops, it will be precisely this loop measure mu, which has been defined. So if you look at alpha fixed, so after a certain time alpha, you have a certain number of loops on the space. And so this is an ideal picture of what you would have. So you have loops, and this Poisson point measure on loops, you can identify it with a set of loops. So it's a set of loops at time alpha, I denote by L alpha. So it's an increasing process. There is more and more loops. And of course, there are also point loops. So you can think of it as a process which is increasing with independent increments. This will be true for the occupation field at each point. But more generally, you can think of it as an increasing set of loops. And the increments are independent. Any question? So what can you do with this? Actually, my point is that these soups are more or less everywhere. That's the basic message. So let me first investigate one thing, which is the clusters made by these loops. So this will be what is a cluster? So you take 2 points and you say that they are alpha related if there is a chain of loops which connect them. So you see these loops, they overlap each other, and so they form clusters. So here you have one cluster, here is another one, here is another one. And you have also trivial ones which are just isolated points. So my point is that these clusters actually have a simple distribution. And they are related to a lot of interesting processes. So let's start with a small calculation, which actually can be deduced of the calculation I did of this measure of the possibility of that a loop connects two subsets. So I computed that with a logarithm. And, well, if you just apply the definition of Poisson process, the probability there exists no loop in this Poisson process of loops, in the loop soup, connected D1C and D2C is actually this quotient of determinant. And I'm sorry, here there is a power alpha missing. It is on my screen, but it is not on yours. Mystery of computer science, you say so? Of computers, maybe not science, but. So I'm losing 1 inch. Well, I'm losing 1 inch. I don't know why. So there is a power alpha here. So you see, this type of thing is easily computable. So as I said, you have clusters, and this cluster defines a partition of the space, which become, when you start with a very small time, very small alpha, the intensity, well, all points are separated, and then as alpha grows, the partition becomes coarser and coarser. Exactly like in percolation, when you let P, the probability of an edge to be occupied increases. So let me denote C alpha as a partition at time alpha. Then from a calculation by exclusion-inclusion, which is similar to the one I described before, given a partition of the space, it's a discrete space, so I give myself a partition, then you can compute the probability that the partition C alpha in clusters is finer than the given partition D1, D2, Di. So you give yourself a partition, and you want the clusters of course, the partition in cluster, not to be exactly this one, but to be possibly this one, or something finer. And so this will be given by a product of determinant of green function, the green function of the open sets, or the sets di, the elements of the partition, divided by the determinant of the total green function. And this to the power alpha again. So this, of course, determines the law of the loop clusters. And so as alpha increases, it's easy to see as new loops are coming that you get a Markov process, C alpha. So what happens when loops are falling is that if this was the partition, there is a loop that overlaps several elements in the partition, and these elements coalesce. So it's a coalescence process. And the jumping rates of this coalescence process are actually explicit and given by formulas of this type. Now, in fact, this formula is nice, but it includes the green functions, and we want to get a formula which is actually easier, where calculations are easier to carry. So this will use Poisson kernels. So I have to recall briefly what are the Poisson kernels, especially analytically, because I think all of you know what are the exit distribution, but let me explain a bit more. So if you take F a subset of your original set X, and you call D the complement, you can compute actually the probability that the P Markov chain starting at X hits F in Y. And this, I denote it HFXY, is just the sum in K. So you look at all possibilities, essentially. So in K steps, you stay in D, and then at the K plus 1 steps, you jump to Y. That's what it says. And so when you compute it, you find the green function at D, the green function of the subset D, multiplied by the conductance, and you have to evaluate this between X and Y. And then it is 1 if X equals Y, of course. Then, so this defines, this is the formula for the Poisson kernel. Now let me use this formula to compute this quotient of determinant that occurs in the law of C alpha, my coalescence process. So I have a product of determinant of GDI over that of G. So I can write this as a determinant of a big matrix in which you have GD1, GD2, GDN as blocks, and then you multiply by G minus 1, just because the determinant of a product of matrices is a product of their determinants, and the determinant of block matrices, it's a product of the determinant of the blocks. So you see, this is not too hard. Now, actually, I replace G minus 1 by what it is, this kind of generator, the diagonal M lambda minus C, and I just compute what it is. And so you see, when you are on the diagonal, you get actually the generator associated with GD1, you get identity on diagonal blocks. But elsewhere, you get the Poisson kernel. You get the Poisson kernels. So what is so good and why is this formula better than the previous one? Well, it's better. So well, you can therefore write. So if I call this this K, this matrix, so this, I get that the probability that C alpha is finer than my given partition, D1, D2, Dn, is a determinant of I minus K to the power alpha, where the K is essentially given by the Poisson kernels between different DIs. So it's an easier calculation because, you see, interior point do not contribute. It's only when there is a connection between di and dj that this is non-zero. So basically, in a lot of examples, except in the case of the complete graph, this matrix will have many more zeros than the original one. Moreover, from this calculation, you see that the percolation model is actually can be viewed as a limit of this model. So the idea is the following. If you take a finite graph with unit conductances, and you take the killing rate to be constant and very large. So it means if the killing rate is very large, it means that loops have a lot of difficulty to exist. Long loops have lot of difficulty to exist. So basically you have trivial loops. And the next, which don't have too much difficulties to exist, are the 2-point loops. So those would just make go and return between 2 points, between two connected points. So if you be a bit more precise, if you give yourself a partition and you denote by EP the set of edges between different elements of the partition, now you have your kappa, which is the killing rate, which goes to infinity. And of course, to have something, you need to put a lot of loops, because most of them are trivial. So you let the time, that is the intensity of the loop soup, grow to infinity too, like u k square. Then the matrix K I computed the equivalent can be easily seen to be 1 over K when 2 points are connected and lie on different clusters, on different elements of the partition. So then when you compute the logarithms at P of the probability that C alpha is finite at the given partition, you get alpha trace the logarithm of I minus K, and this will be minus alpha over K square times the number of edges between different DIs. And so this means that the probability that C alpha is finite than this given partition is E minus U, the size of this set of edges. And this is the probability that the cluster partition of the percolation of parameter 1 minus E minus U is finite than P. This is a probability that for this percolation, all these edges are empty. See? So percolation is a limit case of this model. So let me look at an example. So I take a very simple one. So random walk killed at 0. So what are the clusters? Then they are just intervals, you see. Cluster. They are intervals separated by empty edges. So a question is, what is the distribution of these intervals? So it's actually easy to derive. First, by inspection, you see that these times at which, or these indices at which occurs these empty edges, they form a renewal process, obviously. Therefore, the only thing which is important is the law of the common law of these increments. And of course, it's not obvious that this is infinite. So when I say the law, it is possible that actually you have to, actually everything there is no empty edge. It's possible, and we will see when it happens. But then you can say that the law is degenerate and that pi is carried by infinity. See? So then there is an easy calculation because, well, you look at the probability that one edge given between n and n plus 1 is empty, And it has to be that it is in this set. So this gives you this equation with a convolution of, case convolution of pi, because you have a renewal process. And so the probability that this edge is empty, you can compute by the previous expression. So we can compute these things by the previous calculation. It is a determinant. And so you find 1 over n plus 1 to the power alpha. So if you compute the Laplace transform of pi out of this information, you get that you had convolution, so now you have powers. And here you have the Laplace transform. Again, sum in n of 1 over n plus 1 to the alpha in minus lambda n. So this gives you a formula for what is the Laplace transform of pi. So actually this is a polylogarithm, I think. But from this, you can derive, for example, that the mass, so the probability that actually there is no empty interval. This is 0 if alpha is less than 1. See, here you have the 1 over n over alpha. So obviously there is a change of a transition for alpha equal 1. So this is 0 for alpha less than 1, and this is 1 over zeta of alpha if alpha is larger than 1. Now these formulas are not very nice, but when you take the scaling limit, so just the Brownian scaling limit, what you expect to find is, of course, what will be the clusters for the one-dimensional Brownian motion. And then your renewal process, this was the Laplace transform of the renewal distribution. You get the scaling limit of the renewal process, it's a subordinator. So here you get is a stable subordinator of parameter 1 minus alpha when alpha is larger than 1. So then the clusters will be exactly the jumps of this subordinator. Now let me change a little bit topic. So I let these clusters, maybe at the very end I will talk a little more, but just talk, not do anything. Let me see the relation with the free field. So in general, what is the free field? It was already, I think, introduced, but so you consider your grain function and you note that this is a positive definite function because, in fact, when you compute the energy, the energy of, you can compute actually this expression as the energy of the function which is obtained as the potential of lambda, so by summing gxy lambda y. So this is classical. And so you see that this expression is always non-negative because the energy itself, I defined from the beginning, is always non-negative. So it is the covariance function of a Gaussian field, which is called the free field, and it is defined by the energy. When you are on a finite space, there is an explicit formula for the density of this field. So you see here the energy coming as a weight in the exponential, and the normalization, which is the square root of the determinant of the green function again. Now I have to remind you an easy Gaussian calculation. So you can compute with the Gaussian integral. What can you compute? You can compute exponential of linear and quadratic function, more or less. That's the kind of exponential of formulas you can, which are explicit. So here I do it for a quadratic. So I take my Feynman-Kac perturbation. So I add a positive measure chi And I look at the exponential of minus 1/2, the sum of the square of the free field weighted by chi. And so this can be computed. Well, here I just wrote the expression that comes from the previous one. So you see, just the previous expression, except you have to add E chi. So E chi here is the previous energy to which you add this term. This gives you also a green function. This is the energy which is associated with the perturbed green function. Then this expression from the normalization, you see this is again a Gaussian type expression, so you can actually compute it, and you get the square root of the quotient of these determinants, the determinants of the perturbed green function by the determinant of the original one. So now I want to connect this expression with the occupation field. So I define the occupation field for one loop. But in fact, there is no problem in defining the occupation field for the loop soup. You just add the occupation field all the loops. So I recall you a little formula for Poisson process. When you have a function, positive function on the loops, actually on any Poisson process, you can evaluate the expected value of the sum of the function on each point of the process. So here I take the sum on all loops in L alpha. The expectation of this exponential is given by the exponential of the integral of E minus f of L minus 1 integrated by the intensity measure of the Poisson process. This is just a little generalization of the formula for the Laplace transform of a Poisson process, of a Poisson variable. Now you apply this to f of L to be the sum in x of chi x L hat of x. So the L hat is the occupation field. So this is a function of L, and I take L alpha, so I take the sum on all loops of L alpha. The sum in x is in my function. And therefore, if I apply this, and I go back to my formula P2, so P2 was essentially this expression, but except I had here I had little l, and I had here mu, and I had minus 1. Then I get this quotient of determinant again to the power alpha. And you notice that it is the same type, and actually these are exactly equal if alpha is equal to 1/2. Any question? That's what I wrote here. So you get that the Laplace transform of this occupation field for parameter alpha equal 1/2 is the same as the Laplace transform of 1/2 the square of the free field. Therefore, these two fields have the same distribution. In fact, more generally, if you take any integer k, the occupation field for parameter k over 2 have the same distribution as the square norm of a vector-valued free field, especially for k equal 1, k equal 2, so for L1, you get the complex free field. And so, for example, it follows from this immediately that the square of the free field is infinitely divisible, because this L alpha hat, this occupation field, is infinitely divisible. Indeed, if you take beta larger than alpha, you see that L hat beta minus L hat alpha, this is independent of L hat alpha, because this is actually the occupation field of L beta minus L alpha. Here I take differences of sets. Here I take differences of functions. You see, this is L beta minus minus in sense of sets L alpha. And so these are the loops that have fallen on your space between time alpha and time beta, which are independent of the set of loops which has fallen before. See? That's just the independent increments of this loop Poisson process. So you get this for free. Another noticeable feature of this process L alpha hat is that it is an alpha permanental process. So what are alpha permanental process? Well, it's a generalization which in a sense connects determinantal processes with Gaussian processes, or square of Gaussian processes. So the alpha permanent of the matrix A is the same formula as for the permanent, namely the sum on all permutations of the A1 sigma 1, A2 sigma 2, AN sigma n. But you put a weight which is alpha to the power the number of cycles of the permutation. Then the moments of this occupation field is given by the permanent, alpha permanent of the green function evaluated at the point x1, x2, xn, which can be the same. So for example, if I take 3 points, I get a sum of 6 terms with different factors, alpha 3, alpha 2, alpha. And you see very clearly to what they correspond. You see you have a loop process. So loops are on your space, and there are several cases, several loops that contribute to this expectation. There are cases where actually you look at the time spent in 3 different loops, and you multiply them. There are the case where you have one loop which visits x1. I forgot to draw this one, I'm sorry. And then one which visits at the same time x2 and x3. And so you will look at the product of time spent by one loop, but at 2 points. And then there is also the case where there is a loop that visits these 3 points. And then this will be this expression here. See, when you take the expectation of such a configuration, you will find this. So, more generally, any moment can be computed like that. And when you fix a point x, we really have gamma. What we find is a gamma subordinator, which is given by this Laplace transform, which is a very specific case of the formula before. Now I wanted to explain, but I think I won't have time. Let me see. Well, it's worthwhile. So the case of the simple random walk killed at 0, I explained before. So what is in that case this occupation field? Actually, it is a branching process with immigration. So how do you see that? Well, let me explain what is a branching process with immigration. So at each time, you have an immigration which is a gamma variable, and then you have a contribution that comes from the previous value. So this is where the branching is. It's continuous branching, so it's not a discrete branching. It is you have a population at time n, and this population produces a population at time n plus 1. And this is, the law is such that if you divide this population at time n into 2 populations, the population you get at time n plus 1 would be the sum of the descendants of the 2 populations, and they will be independent. So it means that, in fact, the part that comes from the previous population is obtained by taking a subordinator and at time given by the value of the previous population. So this subordinator here is specific, and the Levy measure is exponential. when you do the scaling limit, namely you take Brownian motion killed at 0, this occupation field becomes a diffusion process with this generator. So you see that the immigration rate becomes constant, and this is a classical continuous branching diffusion Bissell zero square generator. Then you can actually compute again the Laplace transform of this field as a determinant, but this now is a determinant of operators, and this makes sense because this kernel is locally trace class. This works because the green function for Brownian motion doesn't trace class, it doesn't explode on the diagonal. And this will not work in dimension 2, and so we will see that a bit later, what has to be done in that case. Before that, let me briefly give another relation between this process and this loop ensembles and spanning trees, which were described this morning by Greg. So I have to explain a little bit first what is loop erasure. So loop erasure can do it deterministically. So if you have a loop, you can if you have a path, you can erase. In general, a path is not has self-intersections. So you can remove the self-intersection progressively by erasing the loops progressively. So this is what I did, hopefully, in this picture. So you have this path. So you first erase this loop, and then you notice that you have one more, so you erase it, and then you have a path which has no self-intersection. So this one called progressive erasure. So from a path, you get a self-avoiding path and some loops. But usually you neglect the loops. So if I want to be more precise, in my framework, I recall you that I had my Markov chain are actually in continuous time, so they have holding times. So what I will do is I will put all holding times on the loops. And if a point is visited only once, but it will be a trivial loop, that's all. So my self-avoiding paths don't have holding times. They are just discrete paths. Then if you do this, you perform this thing, you can wonder what is the image of the law of the Markov chain using this erasure. So the calculation, so this was introduced by, this notion was introduced by Greg Lawler, and the calculation is easy, so you have actually you can compute the probability, the law of this loop erased path, and the probability that it is this discrete path, so here x0, x1, xn are different, is given by the product of the conductances. This is a weight with the final conductance between 0 and the Earth, or the symmetry, which is given by this killing measure at xn. And then you have a normalizing factor, which is a quotient of determinant, the quotient of the determinant of the green function, and the green function, but with the space x minus this loop here. So it's erased here because of the problem I described to you, but you have to remove this set I called eta. So this, why do you have this formula? Because you see, in fact, when you want to evaluate the contribution of the loops, you see green functions coming. The green function or potential are computed using Cramer's rule, just a quotient of determinants. And this quotient of determinants simplifies. So that's why what is left is the first one and the last one. But then another thing is that conditionally to this erased set, the set of loops you have is related to our Poisson process of loops. It has the same distribution up to some division procedure I will not describe, that the original Poisson process of loops of intensity 1 minus the loops which do not intersect my discrete path eta. Indeed, the loops you erase have to be connected to this. So this is a factor which makes a connection between this algorithm of loop erasure and this Poisson process of loops. And the connection becomes even more manifest if you look at random spanning trees, which are produced with some algorithm. So what you do is you put an arbitrary order on the points of X, you add a symmetry, and you start a chain from the first point. So here I have ordered the points, then I start a chain, and here. I erase the loop, so I have this, which is already a tree. Well. Then you see the first point you didn't use, it was this one, x3, and you start again a path from this point. So I do this, 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 and then I branch into the tree which I already constructed. I could also jump directly here, but this is the root of the tree, so it's still a tree. So progressively, I end up constructing a spanning tree. And the noticeable fact is that the weight of this spanning tree, so the law of this spanning tree, is obtained from the law of loop erasure. And again, by this system of cancellation, you get that the law will be given by the weight of the tree, which will just be the product of the conductances of the edges of the tree, and the normalization will just be the inverse of the determinant of G, the green function. So this is a generalization of Cayley's theorem. So when you collect the loops that have been erased, you see that the set of erased loops is independent of the spanning tree and equivalent up to division to this Poisson process of loops L1. This is just, you check it by the distribution. So what you have to do is, well, you have to perturb the, well, here I don't do I don't give the proof of this. I don't have time, sorry. Let me quickly mention, I will not say much, but let me quickly mention that when you look at the edges of such a random spanning tree, they form a determinantal process. And this is because the probability is that if you look for this law of the random spanning tree, the probability is that certain edges belong to it. This is given by the product of the conductances of the edges times the determinant of a matrix which is obtained from the green function. Just by taking, well, if E, you see the formula is here, if EI is XI, XJ, you take the coupling between XI and XJ, YI, YJ, and then XI, YJ, XJ, YI. So all four possibilities. And then with this determinant, you get this probability. So this is an example of determinantal process. And a particular example is when you look at the final edges, namely those which are directly connected to the Earth, then this will be this determinant involving only the green function and these killing rates. So these points form what is called a Fermi point process on your space X, because it's given by this formula. And in the case of the random walk on Z, which is killed at constant rate, you get a Fermi point process with independent spacings. So you find again this type of independent increments you had in the previous example. It's always simpler on Z. In the scaling limit, if you think of Brownian motion, there will be also spanning trees, which would just be intervals, and one point in the middle connected to the Earth. Not exactly in the middle, somewhere in the interval. And so these points form, again, a Fermi point process, which is actually the Mackey process. And this was actually the first occurrence of determinantal processes in the literature. So you find them again in this theory. So to finish, let me talk only on two-dimensional Brownian motion case, so which is the original loop soup described by defined by Werner and Lola and Werner, sorry. The loop clusters, what are they in that case? Well, they're actually related to conformal loop ensembles called CLE, defined by Sheffield and Werner. And this theory is based on conformal invariance and very closely related to SLE theory. And it occurs, these CLE conformal loop ensembles occur as scaling limits of critical statistical mechanical models. The occupation field doesn't make sense directly, but makes sense if you perform renormalization and smearing. So what is it? Well, what you have to do is take the loops which are not too small, so with the duration of the loop larger than epsilon, and consider, so there is no local time, so you need to actually to look at the occupation field evaluated on a function, so the integral of the function f along the loop. This is what is L hat of f. This is the integral of the function f along the loop. And then you take the sum of all these numbers, because there is only finitely many such loops. And then the renormalization, so the smearing is the fact that you take functions, not points. The second thing is that the renormalization here is very simple. It's just you subtract the expectation. So what you do is really a compensated sum, like when you look at Levy processes with non-negative jumps. And then this converges. So this makes sense. So it's a centered occupation field, if you want. And so what can we say about the distribution of this centered occupation field? We can say that actually we can compute again its Laplace transform by a determinant, but it will not be the same formula since this is not the occupation field. You have to change the determinant. So what you do is that you change the definition of the determinant and you take a renormalized determinant, which is well known as det2. So det2 formally, because none of these terms have sense in the situation I described, det2 formally is the determinant det2 of I plus b is the determinant of I plus b exponential minus trace of b. And therefore, if you look at this, this will exist, this product will exist even when each of these members don't exist, because it's a 0 times infinity thing. And this basically makes sense when B is Hilbert-Schmidt. So the Laplace transform is given by this det2 of identity plus multiplication by square root of f, g, multiplication by square root of f, and this is an Hilbert-Schmidt operator. So this makes sense, and you can take the power alpha. Then again, you see the relation with the free field coming. Namely, for example, for k equal 1, you will get the Wick square of the free field has the same distribution as this renormalized occupation field. So what is the Wick square of the free field? It's again a renormalization. So what you do when you have you want to, first you regularize the free field by taking, so the free field is a generalized field because it's not defined by points. It's defined when you evaluate it on functions. So what you do is to do first a regularization, then you take the square, then you subtract the expectation, and then you have to smear this against the function. So let's see here, x epsilon. So to take a square, you have to have functions. So you first regularize, that's the epsilon, then you take the square, you subtract, you evaluate on a function, and then you remove the regularization, and it exists. So this is this Wick renormalization, which is extremely well known, actually. And you can, so here again, you have the identity in distribution that works. Now, you can do that actually for higher powers using more the extension of this renormalization, which uses essentially Hermite polynomials. Okay, well, and then again, this renormalization works. So I will not inflict you any calculation like that, and I will just advise you to look at the lecture notes 2026. And, thank you for your attention.